Greetings, my name is Kevin Wu, and today I'll be going over the NAE Grand Challenge that my group and I chose. Well, we wanted information that was already given to us so that we could make whatever data that they were providing as efficient as possible based off what they were trying to do. So we decided to go with the Clean Water Data Challenge. The Clean Water Data Challenge was an engineering company that used a filtration process that utilized nanometer scale technology in order to get water as clean as they could. But they figured that it could be even cleaner. So they had a plot, or they plotted all of their positions and times and velocities into one Excel function spreadsheet based off the different time steps throughout the day. So we wanted to make use of the information that they've already given and make it as efficient as possible. But we couldn't do that just by separating the whole thing of what they've already given us. No. We had to dissect and take out little parts and try to make those parts as more efficient and then compile it all together to make a whole running function or a whole running process that would be as certain as possible. So we started by extracting the data into our MATLAB, so using the XLS read function and the atomic data Excel spreadsheet that we had. So that started off too large. We weren't able to use all that data in that one matrix that we were given based off all of the 7,825 rows that they had already in the spreadsheet. So we separated it based off columns and time steps to try to make it as efficient as possible. So in order to make the data as simple as we could to put it into our MATLAB code, and while at the same time making sure that it would still be quite efficient. So when we extracted it into the MATLAB, we found the mean of each time step, the mean of the data at each time step. And for the x velocities and the y velocities as shown over here, this is the x's, and this over here are the y velocities. And then we arrange them into one vector variable for the y velocities and the x velocities, called averages x and averages y. And then we wanted to see the trend in this data, so we plotted it. We plotted it into a figure over here. It would be figure 1 on the top. And that would show the time steps versus the average x velocities graph. And as you could probably tell, the graphs their top one at least had a sinusoidal function or a correlation, which means it would go up and down, up and down, up and down. But the y velocities and the top versus the time steps graph showed no correlation at all whatsoever. So we used that. So we use that. Okay. And then once we saw this data, we also wanted the positions and the times graphs. So we plotted those to see their different correlations and to see how the x's and the y's would differ. And as we were shown through the first figure, the x's and y's on figure 3 also had basically a correlation on the x's, but no correlation on the y's. So we would use that in our function, in our challenge later, to make it more efficient. So after that, we decided to try to single out one data point and make it and follow it through its whole day. Okay, so that means that we would follow it through every single time step, all 26 time steps that we're given, and follow through giving it their x velocity, y velocity, x position, and y position. So we typed in all the data for this one molecule number 1 or 20, and we found all of its data for those time steps as shown over here: x velocity through 26 time steps, y velocities through 26 time steps, positions through all 26, and then we put them into matrices, and then we plotted it as shown through molecule number 120 plots. So this is the flow. The figure number 4 would be the flow of the molecule number 120 through filtration, and that would be its x position and y position correlation graph. And it had more of a correlation than the others because it was all in around the 16.4 to 17 range for the y velocities. And then we plotted the positions of the molecule for the different time steps. The y position on molecule 1 number 120 through each time step was relatively the same, surprisingly, but the x position also had a trend. So the positions, they seemed relatively similar, but the velocities were different, so we made note of that to try to make more efficient. And then once we got all of the data, we wanted to find, since we were given the x velocity, y velocity, x position, y position, we wanted to find the maximum and minimums of each velocity in the x and y direction. So we used a function, the max function, to find the maximum average velocity in the x direction, the maximum average velocity in the y direction. And then we also use the mean function to find the actual average velocity in the x and y direction, so that we could find the correlation between the points and their given data. So next, we wanted to find, since we were given all that data, the x velocities and the y velocities, we wanted to find the positions, or not the positions, but the direction vector at each time step. So that would utilize basically the magnitude of the x and y velocity, and then we would have to find the angle. So we did that using the conditionals, the if and else's. So if someone put in the time step would equals to 1, let's say, then it would put in the data for the x velocity at time step 1, the y velocity at time step 1, into our function, the direction function over here. Oh, hold up. Over here. So the direction function we made, we utilized the division and the arctangent function to find the degrees, and then we square rooted the squares of both of them added together to find the magnitude of the velocity, and that would be the magnitude and the direction that it would be heading. Okay. Now, next, since after we got that, we would have to print it out. So we use the fprintf function to do that. But if the time step, if entered, was less than 0, an error function would occur saying that the time step cannot go below 1 because the data wasn't given for the time steps below 1. And there would also be an error function for the time step going beyond 26 because the data doesn't go beyond 26. So this would be a run of what of the function given. I apologize because this recording device lags my computer when it's using it, so it's hard to type. So let's say at time step number 4, it prints out the velocity on the bottom of the screen. It prints out the direction and the velocity of molecule number 120 at time step 4. So the direction turned out to be 3.7862 degrees with a velocity of 1.4337. So that was time step of 4. And then it printed out the averages on the top and the bottom, which would be constant. The only large changes would be at time, like the different time steps through the conditional statements. So run it again. It would print out all of these figures, and then we would have to type in. They would have the same correlation, and then we would type in again. Let's say time step 0. It prints out the error function. Time step cannot be under 1 because that is what we put in. And then run it again. It takes a while to pop up because the pause function is in use right now. Let's say we want to enter time step 30, but 30 shouldn't work. Error, time step does not go beyond 26 because 30 shouldn't work. So, well, the limitations of this code would be that we basically put it for time step, or not time step, molecule number 120. But if we wanted to print out something for molecule number, let's say 86, it wouldn't work because we only put in the data for time step number 120. So, but we could, since it's basically like the rule of interchangeable parts, we could just replace a couple of numbers using the shift enter function, and then we could do it for time step number 100 or 86 also. But that in itself, not being able to see different molecules correlations throughout the time steps is in itself a rather limiting factor. And we also didn't seem to plot the position, the magnitude of position at the different time steps also. So if we wanted to see that correlation, it should be similar to the y velocity, x velocity based off of physics, but we wouldn't be 100% sure. So that would also be a rather abundant limitation. That is how our code works, and then they could use this information in their own clean water data, the averages of what we were given, to basically plot a mean function through all of the data points, and to find out a routes that would make everything more closer to the average function, that would make it as optimal as possible for the water to be as clean as possible. Thank you, and that is my report.